That seems pretty good. Test, test, test. Guess we should test the audio, but I'm going to do that in just a second here anyway. All right, testing the audio. Seems to be working. Excellent. All right, we're getting stream going. I'm going to get this live, and then I'm going to peace out for just a second to use the restroom and finalize, get the last of the stuff I want. But I want to get the stream fully launched first. But hi, happy Sunday. While I'm getting the rest of the stuff set up, I guess I can mention top of the stream. We always say it: abolish ICE, abolish ICE, abolish ICE, abolish ICE. I have a platform, and it's a tiny one, but it would be unconscionable to me to not use my platform to advocate. And believe me, ICE is not the only problem we need to deal with, but it is an immediate one. I should really, this is a lesson for going forward. I need to do the website before I start the stream. Trying to edit the website while the stream is going just makes everything so slow. It's not exactly clear why. I appear to have plenty of CPU and plenty of memory available. I think it's just a little bit of an optimization or an optimization thing. All right, let's do that. Let's do that. There we go. We're going to work on some Project Euler today. I don't have any problems submitted. So we're gonna jump into problem 1 of Project Euler. We got problem 0 out of the way. We got registered last time. And so now that we're registered, we can actually start the problems proper, which is exciting. Okay, it appears the website is updated. Okay, there we go. So, okay, I'm gonna mute and go off camera for just a couple minutes while I go like use the restroom and get myself like settled for like for the stream, and I will be right back. All right, I am back. Let's make sure I'm still working. Oh, let's get the camera back. Camera's back. Perfect. Hi. Welcome to the Sunday Chill Stream. Yeah, I don't have any questions waiting for me, so I figured we could, like I mentioned before the break, mentioned that we could work on some Project Euler. So let's get that going. I think actually, yeah, we're gonna do this one over here. What's this? Oh, I can close that. Bring this over here, but actually it goes like that. Cool. That seems good. That. And there's that. Okay. I think I have things in position here. It's projecteuler.net. Okay, let's get stuff reshared. We're going to share. Sorry about the yawn being so yawny, y'all. It's been a busy weekend. I am logged in. Yep, Calculus Tutor. Okay. Oh, well, I'm glad this is all hidden and stuff. I shouldn't have gone to the account. I don't know why I did that. It was like a different color, so I just didn't. Okay. What are you doing? Archives. So let's go over to, actually, okay, I'll click on this. And I think what I will do is I will just grab. All right. So just, yeah, in the notes, because so remember what we're going to do is we're going to talk about it. We're going to plan it out. Then we're going to design our solution. And then we're going to write code. All right. I think we went over this one last time, but it was just to show you guys. Oh, I'm so sorry. Okay. If we list all the natural numbers below 10 that are multiples of 3 or 5, we get 3, 5, 6, and 9. Okay. The sum of these multiples, the sum of 3, 5, 6, and 9, is 23. 3 plus 5 is 8, plus 6 is 14, plus 9 is 23. Yep, that checks out. Find the sum of all the multiples of 3 or 5, like these, that are below 1,000 instead of below 10. We could probably do this one by hand and, you devote like a little piece of an afternoon to it, and you could do it by hand. And actually, there is there's actually a pretty fast way to do this by hand. I will also, here, in fact, let me bring this down. Stream will begin soon. That's not true. Stream has already begun. And let me put here, this is our project Euler goal, right, is to create general solutions that could create general solutions and what we mean by a general solution is, so this is, the title is multiples of 3s or 5s. It's saying multiples of 3 or 5 below 1,000. So there are 3 really specific things in here that they could change up to make the problem slightly different. They, instead of multiples of 3 or 5, they can make up multiples of 5 or 7, 3 or 11, whatever, right? 3 and 8. We'll stick to 2. We could further generalize this and say, and figure out a solution that would do it for literally any list of numbers. And then the other thing that could change is this upper limit number, right? That 1,000, that could easily be 2,000 or 10,000 or 783. It could be literally any number. So we want our solution, the solution I want to build here, and actually here, let me put, I just want to put sort of a, here we go. This is our goal. Polo. There you go. This is our goal. Oh, there it goes. So yeah, so we want to solve this for the 3 or 5, but we want a solution that we can put in any pair of numbers and any upper limit, and it would also solve it, right? And so for ours, we'll put in 3 and 5 and 1,000, and it'll solve it. But what we can do is, using the specific example, we can explore this for a little bit, right? We can think about how this works and what's happening. And actually, the example they give is, it's not misleading, but it seems like we could probably do something similar to what we did here. If I zoom out to our last problem, right, where we're just adding together a bunch of numbers, right? So you just come up with a list of numbers and add them together. So we could do a very similar thing, right, where we there we go. We'll make this wider. Okay. Oh, they got connected together. Very good. Okay. Oh, I see. Those two are connected. Okay. Anyway. So we could make a list of multiples of 3 all the way up to 1,000. Make a list of multiples of 5 all the way up to 1,000. Add those lists together, and then take those two totals, add those together. Boom. Except we would be off. That wouldn't be the correct answer. Oh, I posed this to you all last time. Like, do you see why it's not the correct answer? So they give the example up to 10. I want to give the example up to 20. right? So here is, these are our threes, right? And so what we'll do is we'll do 3, 6, 9, 12, 15, 18. Okay, so that's everything up to 20. And now I want to do the same thing. Duplicate that. There we go. Except I want to do it with fives. Right? So we'll do 5, 10, 15, 20. So it's a shorter list, right? Now, if we add all these together, oh, oops, okay. Escape, come out of there, okay. So if we add all of these together, right, 3 plus 6 is 9, plus 9 is 18, plus 12 is 30, plus 15 is 45, 63. And then 15, 30, 50. So what are we at? 113. We would be off by 15. It's not actually 100, what I say, 133. Because notice, when we count this list, we count that 15. And when we count, and when we go to add up this list, we add up that 15 again. So we are double counting the 15s. So if we list all the natural numbers below 10 that are, or all the natural numbers that are multiples of 3 or 5, right? So really we have a single list. We don't have two lists. We have a single list of numbers that are either a multiple of 3 or a multiple of 5 or potentially a multiple of both, because then it is a multiple of 3 or 5, right? But numbers aren't going to duplicate. So like the list of numbers for under 20, the list of numbers we'd add up here, right, is, oops, oh, I see what I did. That this text box is just really wide. Okay. So really, we just have one list. We have a list that's 3, 5, 6, 9, 10. Oh, those are, I was hoping the space would make those a little bit more, separate those a little better. 3, oh my God. 3, 6, 9, 10, 12, 15 once, because we're not every number only appears in the number line itself once, so we don't double count it. So 15, 18. And actually, I shouldn't have put 20 on this one because it says below. This says below 10. I'm doing below 20. This is below 1,000. So 1,000 is a multiple of 5, but we're not going to include 1,000 because it specifically says below. Right? 1,000 is not below 1,000. It is 1,000. Anyway, so this is the list of numbers we actually want to add up. So the difficulty with this one, the trick, the twist, the thing you have to realize to answer it correctly is when you do these multiples, 3 and 5 are going to overlap periodically. How often are they going to overlap? Well, they don't have any factors in common. They're both prime, right? And so they are going to share factors that are 3 times 5, 15. But then notice it's like the third one for the 5s, and it's the 1, 2, 3, 4, fifth one for the 3s. Not a coincidence, right? But then if we go 5 more, 18, 21, 24, 27, 30. If we go 3 more, 20, 25, 30. Every 15 they overlap. So what we need to do is we also need a list, oops, wrong button, of our 15s. And then what we can do is we can add this list, and then subtract this list, right? Because if we add this list, the 3 list and the 5 list will have double counted the 15. So we need to subtract the 15. We also need to subtract a 30 and a 45, so on and so forth, right? So there's actually kind of 3 lists of multiples here. This is how it works for if the 2 numbers that we're trying to find all the multiples of and add together, if they are, what's the word, relative primes? Is that the word? Yeah, okay, yeah, I thought that's relative was the word I was looking for, and that's the right word. So if the 2 numbers are, if the only factor they share is 1, they are called relative primes. They are primes for each other. They're not true primes necessarily, but they don't share any factors. If they did share factors, we would have to do something a little different. So let's, okay. So here's this. Here's the list that this leads to. Let's look at a couple different numbers. So we can see what happens when the numbers aren't relatively prime. Okay, so let's do oops, 6s and sixes and tens. Let's do 6s and 10s. And then that means we don't know what this other list is going to be. So we'll get rid of that and we'll come up here and we'll say question mark. There we go. Let's see enough space. Okay, so 6s. What should we go to? Let's go to 50. 6, 12, 18, 24, 30, 36, 42, 48. Okay, so, and then we're going up to 50, remember. So below 50, so we'll do 10, we'll do 20, we'll do 30, we'll do 40, and that's it. And now look where these numbers first overlap. No 10s, no 20s in here, but boom, there is a 30. So instead of 6 times 10 and 60 being the first number we get, instead 30 is the first number we get. But then this is 1, 2, 3, 4 every 5, and this is 1, 2 every 3, right? Which is similar to this one, which is, oh, all I did is double these numbers. That's really funny. I didn't intend to do that. I was just trying to come up with some kind of lower numbers that would have the properties I wanted. But yeah, so it's not a coincidence that these follow the same pattern as this. They're just this pattern but doubled. But anyway, which means the overlap is also just 15 doubled. But that's neither here nor there really. Just an interesting coincidence. So the question is though, how do we figure out where the list of numbers that we've double counted, right? There is another way to do this where we could go through the numbers 1 through 999, and we could say, and we could just ask ourselves, is it a multiple of 3 or 5. And if it is a multiple of either of those, we keep it in the list. If it's not a multiple of either of those, we get rid of it. That is another way to do this. That's a kind of a brute forcey way, right? Like it doesn't require any super strong mathematical understanding. And so that's what I'm trying to build to is what's the underlying idea here? The underlying idea here is that numbers share multiples, right? 3 and 5 share some of their multiples. Every pair of numbers will have multiples it shares, right? The smallest one might be the first number times the second number, but then multiples of that number will be shared multiples every time. Okay, so we can see that if we want to do this list, we would have double counted the 30s. Oops. So we just need a 30 here. And so we can add this list together, add this list together, add this list together, and then subtract the total of this list from the totals of these. And we'll add up all the numbers that we double counted, subtract them all off all at once, and that will leave us with the true total. However, like I was just saying, we need to figure out how do we find the numbers where the duplicated numbers, right? So 30 and then 60 is obviously going to be it, 6 times 10, right? But notice we have a smaller number, and that's because these have a shared factor. So let's look at their factors. How do I want to do this? Let's move over here. So I will write, so over here we will just say so 2, or I'm gonna write it this way, 6 equals 2 times 3. That's the prime factorization, and in fact I will even write that above this, right? This is prime factorization. Right, so we want to look at the prime factorization of our two numbers. So let's also get 10 in here. And 10 is 2 times 5, right? And now you can see that they share a factor. So if we take their unshared factors, right? So what are their unshared factors? 3 and 5, right? And then we say, okay, so 3 times 5 equals, let's make this wider, of course, equals 15. And so 15 is the double counted factor. 15s are the double counted factors. Right, so simple as that. So whatever our numbers are, the first thing we need to do is figure out what factors they share. We need to break down their prime factorization and then just figure out the unshared factors. We actually don't have to fully come up, like within our process, we don't actually have to fully come up with the prime factorization. What we can do is do sort of and this is going to be a precursor to some work we're going to have to do later. So right off the bat, we can see with this problem number one, we're already having to think about prime numbers, right? Lots and lots of these problems are gonna be helped by us being able to quickly figure out if a number is prime, quickly get the prime factorization, things like that. So at some point, we are going to make a little utility function for ourselves that can do things like that. We'll make a utility function that takes a number and returns its prime factorization. We'll make a utility function that just gives us a list of prime numbers up to some other number, right? All the prime numbers below, 83 or whatever, all the prime numbers below 1,000,000, things like that. Something that we can use to check whether a number is prime, all that sort of stuff, right? Those will become useful. We don't need them yet for this problem. So I like this one because we need to think about it, but we don't have to build anything complicated. We just need to think about it right now. We could build something complicated, but it would be overkill for this problem for the moment. So we're just sort of diving in slowly. Okay. Regardless, we need to find the unshared factors, or find the shared factors, get rid of them, and leave ourselves with the unshared factors. Either way, it is the unshared factors that. Oh shoot! I'm so sorry. I did this wrong. 15s obviously aren't the double counted factors. 30 is, right? 15 isn't even in either of these lists. 15 is in the other list. I saw the 15 and forgot that we were doing 6s and 10s. So, okay, hold on a sec. It's not just unshared factors. What we need is, yeah, it's actually a little bit more subtle than that. What we're looking for is, how do I want to? Oh, this is tough to phrase. How do I phrase this? We need all factors without double counting. So that's ultimately what we need. We need all factors without double counting. Right? So what I mean by that is, okay, between 6 and 10, 2 is a factor, but they both have 1, 2 in them. Right? So we just do 1, 2. We don't do 2 2s. We just do one of those 2s. Then there's a 3. They don't share a 3. There's only 1 3. If we'd been dealing with a number, all right, let me finish off. And then there's also a 5, right? So we will do we'll do 2 times 3. Oops. And that equals our 30. And that's where the 30 comes from. It is the product of, how do you just, what exactly is it here? Because it's not just the unique factors, the factors they don't share. It is the union of factors. This is the union of factors. Ooh, which means we're getting into okay. So this is technically what it is. It's mathematically we call it a union. So what a union is, Right? So we kind of need to define a union. Oops. How did that happen? What? Where am I? Oh, okay. How did that happen? I jumped way over there. Okay. Well, regardless, we're back now. Um, a union is so let's not call it a union, right? So because I don't want to have to explain what a union is. Right this second, it's getting way off into the weeds of what this is. So what it is it's all factors necessary to create both numbers. I like this explanation of it. Here, I'll lower this down. Okay, so in order to make a 6, you need a 2 and a 3. In order to make a 10, you need a 2 and a 5. So we need a 2, a 3, and a 5. All factors necessary to create both numbers, but with no extras, right? So I think that's the easiest way to explain this. Is we need a 2 and a 3 to make a 6. We already have a 2. We need a 2 and a 5 to make 10. We already have a 2, so we need 2, 3, and 5. And there we go. We have everything you need to make both numbers. And really, if we had more than 2 numbers, it would be the same thing. You need all the factors necessary to make all 3 numbers, and you multiply them together. Actually, it would be more complicated than that because you could triple count in the case of 3 numbers, but you could also double count in multiple ways. Each pair of numbers is going to double count some numbers, and so it becomes much messier for 2 numbers. But we could do it. We could figure out the logic. But for right now, we're going to stick with this simpler one: 2 numbers and a limit value, right? But okay, so this is what we need to do. We need to figure out the factors. And if we already have a factor, then we don't need to include it in our list of factors. So here's the thing, though. If we had done a number, so I'm gonna just for example, I'm gonna change this back. If this had been 20 instead of 6, we would have needed a 2 times 2 times 5, right? 2 times 2 is 4, times 5 is 20. And so this list down here would have been a 2, a 2, a 3, and a 5, which meant this right here would be 2 times 2, and that would give us a 60. Oops, a 60. What is happening? 60. Sorry. And that's the smallest number. Because yeah, for smallest numbers, 20, 20, 40, 60. Yeah, 6 doesn't go into 20, it doesn't go into 40, but it does go into 60. That's the first number where they overlap. But no, 6 times 20 is not 60. So it is a lower number than just their product. But yeah, so all factors necessary to create both numbers. We couldn't do just a 2, 3, and a 5 because 2 times 3 times 5, or rather 2 times 5 is not 20. We need an additional 2. Even though the 6 doesn't need that 2, it just needs 1, 2, and a 3, the 20 does, right? And so that's what makes this a little bit tricky, is we have to we can't just, if we figure out our first number is a 6 and we say, okay, well, 6 is a 2 and a 3, we can't just throw out all the rest of the 2's we encounter for our next number. If there's more than one 2, we'll have to also add that to the list, right? And so you can see how this sort of cascades. And about now, that solution I talked about where we just start at 1 and ask ourselves, is 1 a multiple of 3 or 5? No. So we toss it out of the list. We go to 2, not a multiple of 3 or 5, get rid of it. 3 is, so it stays on the list. Then we go to 4 is not, so we get rid of it. We go to 5 is, so we keep it. 6 is, so we keep it. 7 isn't, so we get rid of it. 8 isn't, so we get rid of it. 9 is, so we keep it on the list. 10 is, so we keep it on the list. 11 isn't, so we get rid of it, right? We could just do that. And in fact, code does that very well. But I wanted to point out the underlying principle that's happening here. And why just adding the list together won't work is because we have this shared multiple, right? That any pair of numbers is always going to have a shared multiple, multiple shared multiples. And we're effectively double counting those if we just add up the lists independently. We could also do a thing where we just take both lists, and then with code, it's pretty easy to say, take one list and take another list and write code that just says, okay, in the second list, get rid of any numbers that are duplicates of the numbers in the first list. That's actually pretty easy to do. So there's lots of ways we could go about doing this. I wanted to point out this, how we actually solve this problem of this is the least common multiple, or sometimes you hear it, the least common denominator. That's what we use it for, is to find the denominator often. But yeah, so this is the mathematical process of finding the least common multiple. You do the prime factorization of your two numbers, and then you look at the minimal collection of those prime factors that would allow you to create both numbers, multiply them all together, and boom, you have the least common multiple, the first number where their multiples overlap, and then all multiples of that will be overlapping multiples. Okie dokie. So our question then is, how do we, now that we know all of this, right? This is our background work. Move this over just a tad. This is our background work. And now we can ask ourselves, okay, given this, how this works, how do we want to approach this problem? We've now talked about two actual. I sort of did a thought. I imagined two solutions, and then the solution this is building to is take your two numbers, find the prime factorization, find the factors necessary, right? Like do some sort of logic to only count to only include the factors that are strictly necessary. And that's a third solution, but that involves some additional logic that is not actually fundamental to answering this problem, to getting the correct answer, right? And so as we're going through these problems, that's what we're going to have to ask ourselves. I want to dig into the math, see what the actual math says, but just because we figured something out with the math doesn't mean that we have to use that in our solution, right? Because it might require a bunch of additional logic and work. And what we've talked about here will come in handy for later problems. I've done the first, I don't know, dozen or so of these problems like in the past. It's been a little bit, but like 10 years. So I don't hardly remember them, and I definitely don't remember my specific solutions, right? All right. So with this in mind, like looking at all of this here, so we need to come up, and actually, how did I write this down last time? That's what I'm curious about. Oops. School this, process steps. That's what I called it. Okay. And so notice this is how this process is going to kind of go. We'll get the problem, we'll read through it, we'll think about it, talk about it, we'll write some stuff out to explore the math of it. And then this is our, I'm going to start calling it maybe a solution sketch. Okay. Oh. I clicked out of it, so of course. Okay. So, okay. Where do we want to start? How do we actually want to approach this? Do we want to do the thing where we just list out all the numbers and get rid of them if they're not multiples? We could do the thing. It's easier to build. I mean, we could just build a list of the multiples. Like we don't have to get rid of them for 3 or 5. The harder part. And then we honestly, I think then we just compare them and get rid in one of the lists, get rid of the duplicates, right? So make a list of multiples below limit, make lists of multiples below limit of both numbers, right? Oh, I guess I should turn these into, there we go, steps. Okay, so that's step 1. Then what we want to do is we want to, the bigger number is going to have the smaller list. So there will be fewer numbers to remove from that list. So, but there's more numbers to check in the bigger list. Huh. This is the thing we'll probably have to figure out once we get to code, see what actually feels more efficient. Remove all duplicates, or here's what I want to do. Compare lists, removing all shared numbers from one list. We don't want it from both lists, right? Some lists, some for list subtotals, some list subtotals. Boom, that's our process. 4-step process here, right? Not too bad. Oh, we're getting on to noon. I don't think I have enough time to actually implement this out in Python. I will say something I've been thinking about doing is doing these solutions in Python, and then maybe also doing them in like a random language, right? Like I could make a list of languages that I'm interested in doing solutions in, and then I could just like randomly choose from that list, right? So we could have Haskell and Rust and Fortran and C++ and C, and there's a weird think there's a language called Cheeseburger or Lolcat or something, which I've written stuff in. It's just a toy language. It's just like a joke language, but it works. It compile it like yeah. Um, JavaScript, Java, right? Like there's all sorts of languages. Frickin' R, um, F sharp, things like that. I don't even think F sharp is actually used that much in industry anymore. I think it's been replaced by R. Dart, right? Um, C sharp. All the we could take all of these languages. Old school basic, right? Um, that could be fun. I don't know. I know Fortran a little bit. I've worked in a little bit of Fortran. I don't know Haskell. I don't know Rust. Um, I've never actually used Java. I've used lots of JavaScript. Um, I've used a lot of Dart because I've done a lot of Flutter. I've built a lot of stuff with Flutter. Um, Go is another language. Is a Google language. There's TypeScript for Macs. Um, Things like that. Anyway, it occurred to me as a way to sort of practice with other languages and just like and challenge myself with languages I'm not familiar with. Right? I don't think I'm going to do that initially. I think maybe we'll get to a certain point and maybe I'll either start adding that in as we work through problems, or I'll go back and revisit older problems that I've already done in one language and try to redo them in some other language. Right? For now, though, we have our solution sketch, right? We looked at we investigated the mathematics of it, and this seems to me to be kind of a pretty direct solution. Um, and we'll get into this prime factorization stuff for subsequent problems. There are going to be problems where we can't escape this. This is, in fact, the easiest way to go about doing it, is to actually figure this stuff out. But we'll get there, right? The first problem's not intended to be one that requires you to build a bunch of utility stuff for yourself. So with that in mind, I think next time what we'll do, maybe Wednesday. I think Wednesday. Um, I think I might I think I might change my schedule, especially as we head into summer and it becomes less critical to worry about the local school schedule. But yeah, I'm really enjoying this, and I've been wanting to get in here and do it. And since I told myself, I sort of created the standard for myself that I would only work on this on stream. Because this is a thing that I'm kind of doing that's fun. Working on stuff like this is fun for me. This is legitimately like an enjoyable thing. It's almost something I enjoy more than like video games. It sort of exists. It satisfies that same thing for me. And in a lot of ways, I enjoy this more. Um, so yeah, so I've been wanting to do this, but I told myself I'll only do it on stream, which means if streaming's just not like viable, or just I can't stream, then I'm like, well, I guess I can't work on it then. So my hope is that it feels like this is going to pull me into stream more often, and I'm super glad about that. So anyway, let's go ahead and leave it there. When we come back, next time we will, since we have our solution sketch, we'll just build it, and then we can move on to the next problem 2, and start this process over. Right? We'll look at the problem, we'll read through it, we'll think about the mathematics of it. Yeah, this is yeah. I do enjoy this. I hope it is. Well, nobody's really watching, and so it is mostly for me, and so that's all that really matters. Until next time, hopefully Wednesday. I hope you all have a good rest of your weekend. See you later.